Hello, and welcome back to the Cosmic Companion. This is a special episode, as it marks both the first show to start our third season, and this installment is the first partly recorded in our new studio. But most of all, what is special is that we take an inside look at the James Webb Space Telescope. Scott Lambros, NASA's Instrument Systems Manager for this revolutionary telescope, joins us this week, giving us his first-hand story of this next-generation space telescope. Comet NEOWISE is visible in the evening sky starting this week. The comet has already developed a short tail and can be seen low on the northwestern horizon starting about an hour after sunset. This display should last a couple of weeks as the comet heads back out to the outer solar system. See it now because it won't return again for another 6,000 years. Visit the Cosmic Companion online for updates on this comet as they unfold. The origin of the moon is usually explained through a collision between the young Earth and a Mars-sized body billions of years ago. But a glancing glow would have left the moon with few metals. A new study finds the moon is richer in metals than previously believed, suggesting something about this origin story may not be correct. This finding may be explained if the impacts are more direct than previously believed, or it may have happened when the Earth was still largely molten. Or perhaps the cooling process of the moon as it formed was more complex than originally suggested. An exoplanet discovered 730 light years from Earth is highly unusual in that the core of the planet is exposed to space. Our own planet has a metallic core surrounded by largely molten rock covered by a thin, cool crust. However, TOI 849b is the first planet ever found with a core exposed to space. This planet is roughly 40 times larger than the Earth and orbits its sun-like star once every 18 days. Speaking of the Sun, it appears our stellar parent is not the center of the solar system after all. Any objects orbiting with each other circle around their common center of gravity, called a barycenter. By observing distant pulsars, astronomers were able to calculate the location of this barycenter for our solar system for the first time, finding it sits just outside our local star. Today, we have the honor of being joined by Scott Lambros, NASA's Instrument Systems Manager for the James Webb Space Telescope. This week on Astronomy News with the Cosmic Companion, we are just plain overjoyed to welcome Scott Lambros. He is the Instrument Systems Manager for the James Webb Space Telescope at NASA. Welcome to the show, Scott.
Thank you very much.
Thank you. So can you tell us a little bit about what is the James Webb Telescope and what do you hope to accomplish from it?
Okay, it's a telescope that will go into space. It's the first deployable telescope that will go into space. Deployable means the mirror is too big to fit into a rocket, so it's made up of 18 hexagonal mirrors, segments we call them, so that the 3 on each side can fold back and then it fits inside the rocket. It's 6.5 meters in diameter. It's very large for a space telescope, the largest that we know of so far. And it has 4 instruments that it collects the light and sends it back to 4 instruments that are built in Europe and Canada and the United States. It's a cryogenic observatory, which means it operates at cryogenic temperatures, which is very cold. So the instruments operate at around 40 Kelvin, which is 40 degrees above absolute zero, which is about minus 390 degrees Fahrenheit. One of the instruments has a particular cooler on it that takes it even down to about 7 Kelvin, 7 above absolute zero. The reason it has to operate cold, and I'll just keep going on if you want to interrupt and ask some other questions.
No, please.
Okay, the reason it has to be so cold is because we're looking into the infrared. Mm-hmm. So whereas Hubble, for example, looks in the visible range, we look in the infrared, which means we can see objects that are further away. Because of the expansion of the universe, everywhere you look, the universe is expanding around us. It's like being on the edge of a balloon. And as the balloon blows up, you look in any direction and things are moving away from you. And the further away they are, the faster away they're moving. And because of this expansion of the universe, the light that's coming to us is stretched out. So that's where it gets stretched from the visible into the infrared, particularly for the objects far away. So we'll be able to see objects that are much further away than Hubble. And we're talking about 13.5 billion light years away. So we're seeing things in the past that are 13.5 billion years old. That's a couple 100 million years after the Big Bang. For your question, what will it do? One of the things it will do is we're trying to see some of the, what we call first light, some of the first stars and galaxies that were ever formed in the universe. So that's pretty cool.
That's pretty cool, about 40 Kelvin.
Yes.
And do you need to cool down some of these instruments even further because of sunlight hitting the instruments?
No, so there's no sunlight hitting the instruments. We have a tennis court-sized sun shield.
Oh, right.
And so that's between us and the sun. So you have the sun shield here, sun on this side, and then the mirrors and the instruments are all on this side. That sun shield is 5 layers, and there's a temperature drop of about over 500 degrees from the warm side to the cold side. So that keeps everything cold. But any heat, even heat from the electronics that are nearby, is noise on the detectors when you're looking in the infrared, because you're detecting heat. So, so that's why it has to be that cold. And the one that's colder has it's a mechanical, we call it a cryo cooler, and that takes it down to about 7 Kelvin, and that's because it goes further into the infrared. So if you know your wavelengths, the three of the 4 instruments operate in about 0.6 to 5 micrometers. That's the wavelength, okay, just after the visible. And then the other one is from 5 to about 28.5. So it goes further into the infrared, so it gets even more sensitive to heat that's coming off of somewhere else other than what you're looking at.
Right. And other than pure distance/time, what will the Webb telescope be able to do that the Hubble cannot?
Okay, because it's the distance, and then also because we're in the infrared, it can see through clouds and dust. There's a kind of iconic picture from the Hubble. It's called the Pillars of Creation, where you see these huge, big clouds of dust. And in the visible range, you can't see through them. When you look in the infrared, you can see right through them. You see all these hundreds and thousands of stars and galaxies that we wouldn't otherwise be able to see. So again, because of the infrared, we'll be able to see a lot more because we can see through those clouds and dust. The other thing is we will be looking for planets. And we have advanced coronagraphic tools on the James Webb. So we'll be able to see planets that are closer to stars. Just to give you an example of how that works is we have masks that go into the field of view of the instrument, and it will cover the star so that you don't get the brightness of that star. Mm-hmm. And then so you can see something that's much dimmer that's circling around the star, like a planet.
So you'll be able to use it to get direct images of exoplanets?
So you can get direct images, yes. You can also infer it by it's transiting. You can measure the amount of light that's coming off the star, and as the planet moves in front of it, the light will dim some, so you can see it that way. But yeah, direct imaging too, and also we have spectrographs on board, so they'll be able to, kind of in the same way as the planet moves in front of the star, it changes the spectrum that you see. The spectrum is the light dividing up into different wavelengths, so you can determine the chemical composition. So we'll actually be able to determine the chemical composition of some of the atmospheres of some of these planets.
Right. Of course, that's pretty exciting because you can look at these, you can look at the atmosphere of some of these exoplanets and potentially even look for things like methane,
right,
which could theoretically suggest life.
Right, exactly. And hopefully we'll be able to get closer to the star, so they'll be in what we call the habitable zone, which is not too cold, not too hot, kind of like where the Earth is compared to our star. Mm-hmm. Again, so these have the potential to support life as we know it.
Right. And how much do you see the Webb being used for exoplanets compared to cosmology or galaxies? Do you see output being?
Well, I don't really know the answer to that question, but I do know that anybody can apply to use the telescope. So after the beginning, when all the scientists that have been working on this for 20 years now, they get to look at some of their pet projects, and it's open for anybody to propose. So people can propose, and so the makeup does depend somewhat on what kind of proposals that they get.
Mm-hmm. And can you just give us a brief rundown of some of the instruments that are aboard the Webb and
Sure.
What excites you about them?
Sure. We have 4 instruments, and so I'll go through them. One is called the NIRCam. It's a near infrared camera. It operates for the most part like a camera. It's being built by the prime contractors Lockheed Martin in California, and the principal investigator and her team is in the University of Arizona in Tucson.
Just down the street from my house.
That's right. And then there's what's called the mid-infrared instrument, MIRI. That's built by a consortium of 10 different countries in Europe, plus JPL in the United States, Jet Propulsion Lab. Mm-hmm. So 10 different countries actually build pieces of hardware, and it all comes together. That's the one that goes further into the infrared, and has the cryocooler as well. Mm-hmm. Next is a near spec. It's a near infrared spectrometer. That's the prime contractor there is Airbus in Germany. So they built it through ESA, which is the European Space Agency. Mm-hmm. Parts of that are built at Goddard, which is where I'm from, where I work in Maryland. The detectors and the microshutters. Talk about the microshutters for a minute, but those pieces are supplied to that instrument. So the microshutters are a technology development as well, and it's an area, 4 or 5 inches square that holds 250,000 little windows, and the windows are slightly bigger than a human hair by about twice that long ways, and you can open them programmably. So you say which ones you want to open, and you open those, and so it can look at, we say on average of about 100 different stars or targets that you want to look at on orbit. So you can get the spectrum of that many different objects as opposed to what we've been doing, which is using a slit. Slit can look at one small little area, a star or maybe a star in the neighboring area. So this is a big improvement there. So that's a near spec, and then the last instrument is called it's got two parts to it. One is called the fine guidance sensor, and the other is called the NEAREST. The fine guidance sensor is really part of the attitude control system. So it doesn't do science per se. It takes very, very accurate pictures of what we call a guide star. So that's a star that's known. It's in the star catalog that we have, so we know exactly where that is. And it takes those pictures and it sends them to the attitude control system. And they use that to keep the telescope pointing exactly where you want it to point. It sends those pictures 16 times a second in a very tiny area. It's 8 pixels by 8 pixels, and the pixel is about 70 milliarc seconds. So it's about half of an arc second square is where that picture is. It's very accurate. And then the Canadians wanted a science contribution as well. So they have on the other side of the bench of that FGS instrument is something called NEAREST, which is a near infrared imaging and slitless spectrograph. So it does imaging and spectroscopy as well. And it will be able to look at bright stars and also planets. It will do the spectroscopy of the planets too, as they get closer to the stars. So
it's
it's
super.
kind of a rundown.
And so just thinking in terms, I don't know if there is a way of doing this, but is there a way of thinking of the Webb in terms of its resolution as if it were a digital camera, and how would that compare?
And say again?
I said, is there a way of thinking of the images as, or maybe through an instrument as having a certain resolution like a digital camera?
Yes. So like some of the spectrometers have a resolution of 100 to a couple thousand. I'm not sure that tells you a whole lot. The resolution of the images, because it goes down to the pixel level. So like I said, for the FGS, the pixel is about 70 milliarc seconds. An arc second is a 60th of an arc minute, which is a 60th of a degree. And so I think that's the resolution that tells you something about the kind of resolution you'll get from the images. On the NearCam, they have a shortwave channel and a longwave channel. The shortwave channel goes down to about 32 milliarc seconds resolution. So, and that's actually used for something we call wavefront sensing, which is a way that we align the telescope. So I said it has these 18 different mirrors. When they get up there, they have to look like one smooth surface. Mm-hmm. And we do that by a process called wavefront sensing. Each of those mirrors has 7 actuators, 7 motors on the back that can move the mirrors. And one of those 7 actually can change the shape of it. But we're talking about, the smallest motion these motors can make is 8 nanometers. So we're talking very small motions, but that's what you need to make this thing get the sensitivity that we need to keep it smooth. It's smooth to about an order of about 20 nanometers.
And so go ahead.
Yeah, well, I was just going to say, so in this process of wavefront sensing, which takes a while to do, and we've spent a whole lot of time to figure out how to do this, we use the NearCam instrument to take images, and you see how it goes, and then you tweak it a little bit and you take another image. So that's what we use the shortwave channel for, because they do have a good resolution of those pictures.
That's great. And, this is a very complex machine. Of course, it was originally meant to launch in 2007. And of course, now we're sitting, 13 years later. Can you tell us a little bit about what's caused delays and what challenges you folks have faced?
Sure. So after it was 2007, we did have a reprogramming, which took a couple of years to do. So I think we got much closer to today where we were. And that really took into account the size of the mirror, the technologies that we had to develop, and the budgets that we needed. So we had to make sure the budget matched what we needed. And so we got all that sorted out, and we got something closer to where we are now. And then we ran into a couple challenges, like any project does. We've had our share of hardware issues, but we've overcome all of them so far. And it's a big and complicated telescope. We build it up by looking at in piecemeal. So all the instruments are built at their sites. They deliver them to Goddard, and then we put the instrument package together. We test it. We had 3 of those cryogenic tests where we go down to 40 degrees Kelvin at Goddard. And then we integrate that at Goddard with the mirrors. Now it's too big to fit in the Goddard chamber, so we shipped it down to Johnson Space Center in Houston. And we tested in the cryogenic chamber there. And then, so we've done that, and then we shipped it out to Northrop Grumman in California, where they're doing the final tests there. So it's just a big, complicated beast with lots of testing. It doesn't get serviced like Hubble does, so we have to do the testing to make sure everything works. Most everything is redundant, so if something fails, it has a redundant backup. And so that's where we are now.
Right, and of course, one challenge that we're all facing worldwide is the COVID-19 pandemic.
Right.
Tell us a little bit about how that has affected the project and what you folks are doing to try to continue work through safety procedures.
Sure. So, so we were on path to meet our launch date of March 2021, and then the COVID hit. So, so we obviously have slowed down. Northrop Grumman actually has been working the whole time, not to the same level. You know, they have fewer people working, and if people don't feel comfortable working, they don't come in, and so we'll defer some of those tests. So we're trying to be very sensitive to the overall safety of people, but it has delayed us. And so what we're doing now is looking at, we're actually increasing now. We're getting back in sync a little bit. We're doing more of testing. We have a big test coming up, actually, which I'll be out on the West Coast for starting next week. It's a comprehensive system test of the whole observatory. What was I going to say? So we're monitoring all the protocols. So we're looking at now what the impact has been of the slower rate that we're going. And that's taken us a couple of weeks, and then we'll come up with a new launch date, run that by headquarters, and then in the middle of July is when there'll be a headquarters meeting to decide on the new launch date. So I expect shortly after that, they'll make a formal announcement.
And of course, you know, that is the big question that is on the minds of everyone who's been following this project is, when is this telescope going to get off the ground?
Right.
And do you have any idea of when that might be?
Stay tuned for the middle of July.
Middle of July? Oh, for the middle of July this year for the announcement for next year?
Oh, yeah, we're not going to launch in the middle of July.
Right, yeah, right.
That's
Okay.
when the announcement comes.
Right. And do you expect that we could still get off the ground in 2021, or do you see it going longer than that?
I don't see it going longer than that, but you know, anything more than that, I can't really say. It really depends on looking at all the different aspects and where we end up.
Super. And is there anything else that you think people really need to know about the James Webb Space Telescope?
So a couple of interesting things. If the telescope is on the ground looking at the moon, it can detect the heat of a bumblebee.
Wow.
So that gives you an idea of the sensitivity. I think that's the main thing. just some kind of fun stuff to know. We feel like we've gone through every natural disaster that we could possibly have, mostly during when we do our cryo tests.
Mm-hmm.
The ones at Goddard, we had what we call Snowmageddon. We had several feet of snow. We brought out mattresses and people slept in offices. And so that was kind of fun. We've had lightning strikes during the test. These are tests that you can't stop, right? So we had 2 lightning strikes actually during one of the tests. Through the electronics in the building a little haywire. We got through all that. Then we went to Houston and we ran into Hurricane Harvey. We had over 50 inches of rain in a couple of days. And now we're in a pandemic. So I'm just waiting for the plague of locusts to come.
As they say, space is hard.
What's that?
So as they say, space is hard.
Yes.
All right.
Makes it interesting.
Exactly. Well, thank you very much, Scott. It was wonderful to have you on the show.
You're very welcome. Thank you for having me.
All right.
Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of The Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on Comet NEOWISE and other space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.